Hi, this is Mrs. Kidman, and in this video, we are going to be discussing how we can write polynomial equations given the zeros of the polynomial. So before we get started on that, I do want to talk about one type of theorem. Now, this theorem is kind of two theorems combined together, but basically what it says is the irrational conjugates theorem or the complex number conjugates theorem both state that if a polynomial has only rational coefficients, then the solutions are both elements of the conjugate pairs of either the irrational or complex numbers. So for example, if 3i is a solution, then so is negative 3i. Similarly, if the square root of 3 is a solution, then so is the negative square root of 3. Oh, we want to make sure we have that there. So is the negative square root of 3. Similarly, if we have anything along those lines, we can always use that conjugate pair there. So what we're going to do is we're going to take an opportunity to write polynomials, and we only are going to want them to have rational coefficients. So we're going to be applying this irrational and complex conjugates theorem in order to write these. So let's take a look at this first one here. We want to write a polynomial function of least degree that has a rational coefficient, a leading coefficient of 1, and the given zeros. So our zeros here are going to be 3, 0, 1, and 2. So using that idea, we want to figure out what is a polynomial function where all of these are the case. Well, when it's zeros, zeros is another name for our solutions. So what that means is that x is equal to 3, x is equal to 0, x is equal to 1, and x is equal to the square root of 2. Now, when it comes to writing a polynomial function, we want to write it using its factors, and its factors are when the polynomial is not equal to something else, but when it's equal to 0. So for example, here, when we have this x equals 3, what I want to do is I want to take x equals 3, subtract 3 from both sides, and get that x minus 3 equals 0. So this is my factor, this x minus 3, that I'm going to put into my polynomial function here. So using that first piece, I know that f of x, my function, is going to be x minus 3. And then if x equals 0, then we're also going to have an x. If x is equal to 1, then we have x equals 1 equals 0. Or not x equals 1. We want to turn that into x equals 0, so we subtract 1 from both sides. So x minus 1 equals 0. So then we also have an x minus 1. We have our square root of 2. Notice how our signs just change here. So this will be minus root 2 on both sides. And we get x minus root 2 equals 0. And then because it is a conjugate pair, that means if x minus root 2 is a factor, then x plus root 2 is also a factor. Now we can rewrite this in a lot of different ways. One way you might see it is typically our x here is brought to the front. So you might see something like x times x minus 3 times x minus 1 times x minus root 2 times x plus root 2. Similarly, we can also combine this conjugate pair here into an x squared component. So if we were to FOIL this back out, we would get x times x minus 3 times x minus 1 times x squared minus 2. Because if we set that equal to 0, that's how we get those two solutions. So I do not care which way you write it out, but we want a polynomial that has this property. Now we can multiply these all out, and that's totally fine. I left mine in factored form, so I didn't have to multiply it back out. Let's take a look at 3 more examples here where we are writing a polynomial function of least degree that has rational coefficients, a leading coefficient of 1, and the zeros given below. So in this case, we want to do that same sort of thing. Now I want you to notice here that as we wrote out those factors, if x equaled 3, then the factor had x minus 3, so it was the opposite. If x equaled 1, then it would be the opposite of a minus 1, things like that. So when we go to do this, rather than having to say x equals negative 5 and adding 5 to both sides every time, we notice the pattern here is that our signs switch when it turns into a factor. And we know this because that's a way that we solve when it goes from a factor to a solution. So we can say, I know that we're going to have a plus 5. I know that if x equals 7, we're going to have an x minus 7. We're going to have an x plus 1. And we're going to have an x plus 3i. Now remember, if we have a plus 3i, we're also going to have its conjugate. So what is our polynomial function here? Well, we are going to get x plus 5 times x minus 7 times x plus 1 times x plus 3i, and our x minus 3i. Now, just like before when we had those two radicals, or irrational numbers, I'm actually going to combine my complex numbers as well. And so this actually can be written as x plus 5 times x minus 7 times x plus 1 times x squared plus 9. And the way that we get this is we end up squaring both of these terms, but because it's an I, if they have opposite signs, we change it to a plus. Okay, that's kind of how those combine. If we were to FOIL those out, we would end up simplifying into x squared plus 9 as well. Okay, so let's take a look at this next one here. We want a comma here, but we've got -1, 2 with a multiplicity of 3, 5i, and root 3. This is going to be our last example here, but what we want to do is write this polynomial function. So this one's going to have a lot to it. So our f of x, if it's -1 here, that means we have an x plus 1. 2 with a multiplicity of 3 means that I have an x minus 2, but I've got 3 of those. Okay. Our 5i tells us that we have an x minus 5i. It also means it has its conjugate pair, so the x plus 5i. And our root 3 tells us we have an x minus the square root of 3 as well as an x plus the square root of 3. So what is our function here going to look like then? Well, if we were to write it all out, we would end up getting x plus 1. I'm going to write this x minus 2, but where it has a multiplicity of 3, I'm just going to put an exponent of 3 here. We've got our x minus 5i, our x plus 5i. We've got our x minus root 3, and our x plus root 3. Now, just like in our previous examples, I'm going to combine these two together and combine these two together just to make it a little bit simpler to look at. So in this case, we're going to end up getting x plus 1, x minus 2 to the power of 3. These two will end up combining to x squared plus 25 if we were to FOIL that out there. And if you would like to see that FOILing, I'm going to write it right here. We get x squared plus 5i x minus 5ix minus 25i squared. And these in the middle will cancel each other out. So we get x squared minus 25i squared. But remember, I squared is defined as -1. So x squared minus 25 times -1 is how we get that x squared plus 25. And then these two we can FOIL that same way. The middle terms cancel. Negative root 3 plus positive root 3 is just root 3. So we end up getting x squared minus 3. And this is what that polynomial can simplify out to. Pretty crazy, right? So that is how we can go through and write a polynomial function of least degree that has rational coefficients, a leading coefficient of 1, and the given zeros. Now notice how these ones were all least degree. I can add as many other factors to this as I would like, but it's not going to be the least degree unless it just contains these factors that are required along with their conjugates. Additionally, we can multiply that whole thing by any number and change the leading coefficient, but in this case, where they all were an x, that's what made a leading coefficient of 1. So if you have any questions, don't hesitate to reach out, but that's how we can write polynomial functions given their zeros.